Let's jump right in. If you follow the space, you already know that AI is definitely not magic. It's actually just highly structured math operating kind of like a master toolbox for recognizing patterns. When you hear about these massive machine learning models predicting housing markets or filtering your company's inbox, well, it's all driven by exact mechanical processes. So in this explainer, we aren't just looking at the flashy outputs. We're literally opening up the machine learning toolbox to examine the specific instruments driving all these predictive systems. To keep things structured, we've broken this explainer down into 5 core areas. First, how machines actually learn. Then, categories versus numbers. After that, we'll dive into the machine learning toolbox itself, followed by choosing the right tool, and finally, we'll wrap up with the future of AI.
All right, section 1, how machines actually learn. Let's start right at the foundation.
So how does AI actually learn? It's a fascinating question. At its core, a machine goes from a total blank slate to an incredibly accurate prediction engine using something called labeled data. You can think of this as a giant exhaustive answer key. Instead of basic rote memorization, it's more like we're feeding an algorithm tens of thousands of historical examples complete with their known outcomes. This literally forces the model to calculate the specific mathematical weights that connect the inputs to those outputs.
And that whole process, that is supervised learning. It's the engine powering the vast majority of enterprise AI we see today, from complex pricing algorithms to those really robust spam filters we all rely on. The absolutely crucial takeaway here is that the machine is entirely supervised by human-provided labels during its training phase. Because of that, our historical data becomes the ultimate ceiling for its future accuracy.
And this completely maps out the blueprint of the process, which happens in 3 clear stages. First, we feed it data. Let's say the square footage and location of 1,000 houses, along with what they actually sold for. Second, the machine learns the internal relationships. It calculates exactly how square footage or a specific zip code mathematically dictates value. And third, which is the real payoff, we introduce a brand new, totally unseen property, and it instantly spits out a highly accurate market prediction based on those learned weights.
Moving on to section 2, categories versus numbers. Before we start pulling specific algorithms out of the toolbox, we have to understand the 2 main jobs these tools actually perform.
Basically, every tool in the supervised learning belt does one of 2 things. If you're sorting data into distinct buckets, like say flagging a medical scan as positive or negative, you're using classification. On the flip side, if you need to predict a continuous sliding metric, like tomorrow's exact temperature or next quarter's revenue, well then you need regression. So it really comes down to categorical buckets versus continuous numbers. Every algorithm specializes in one, or sometimes both, of these specific tasks. That brings us to section 3, the machine learning toolbox. With those 2 distinct jobs in mind, let's actually look at the specific algorithms in play here. Let's contrast our first 2 tools right off the bat. Linear regression is basically your straight edge for predicting continuous numbers. It's fast, it's clean, and it's highly interpretable. But then we have logistic regression. And you know, despite the name having the word regression in it, it's actually a classification tool. It works by calculating probabilities to determine, for instance, that there's a 95% chance a transaction is fraudulent. That makes it an absolute industry standard for binary sorting tasks. Building on that logic, we get into decision trees. These are highly interpretable visual rule makers. They're absolutely perfect for things like loan approvals, where your logic actually needs to be transparent and explainable. But they do have a pretty fatal flaw. They tend to overfit their training data. Basically, they memorize the data rather than learning to generalize. So to fix that, a random forest generates an ensemble of, say, 100 different trees and relies on the wisdom of the crowd. You trade a little bit of that interpretability, but you gain a massive boost in accuracy and structural robustness. Real game changer. Rounding out our specialized tools here, we have K-nearest neighbors, or KNN. This one classifies new data points purely based on their proximity to known examples. It's brilliant for grouping similarities in small data sets, but it does get pretty computationally bloated at scale. Then there's the support vector machine, or SVM, which mathematically maps the absolute optimal dividing boundary between complex classes. That makes it a total powerhouse for high-dimensional data. And finally, naive Bayes uses pure probability to quickly categorize text. It is blazing fast for things like spam filtering, even though it naively assumes every single feature acts completely independently of the others.
And finally, we have the heavy-duty power tool, artificial neural networks. When you graduate to highly complex, non-linear problems, like real-time language translation or advanced computer vision, this is what you deploy. They are literally the foundation of deep learning. But of course, that kind of power comes with a steep tax. They're notorious black boxes, and they require massive oceans of data, plus incredibly expensive compute power to run effectively.
Okay, Section 4. Choosing the right tool. Let's ground all of this and see how these abstract tools are actually applied in a real enterprise scenario. If you are architecting a hospital disease prediction system, you don't just use one single algorithm. You deploy a whole ecosystem based on very specific constraints and trade-offs. For example, you might map logistic regression to simple, fast disease classification, but you deploy decision trees for frontline medical support simply because doctors require that transparent, interpretable logic. Now, for robust diagnostic accuracy where you absolutely cannot afford an error, that's where you bring in the random forest. And for parsing thousands of highly complex, high-resolution MRI scans, yep, that is exactly where you unleash neural networks. Which brings us to our final part, Section 5, the future of AI. Let's look ahead to what all of this actually means for tomorrow. I want to leave you with this somewhat provocative thought to ponder. We've seen that modern AI is incredibly powerful, and it's transforming entire industries. But remember step 1, supervised learning strictly requires human-provided answer keys. No matter how advanced our neural networks become, they are fundamentally tethered to the labeled data we feed them today. If our datasets are flawed, if they are systematically inaccurate or incomplete, tomorrow's AI is simply going to scale those exact same errors at terrifying speed. So the real question isn't whether your algorithm is computationally powerful enough. The real question is, what hidden gaps and blind spots are sitting right there in the data you're about to train it on?